So 5-4 isn't really anything too new. It's really the ideas from prior lessons all combined into one. So basically we've learned a couple things so far. When we solved by graphing, we would graph the problem and we'd get a solution. Like here's our solution that I just highlighted, 2, 3. The solution is where the two lines meet. So this graph has one solution. In our next graph, if I'm going to look to see where the two lines meet, it's pretty clear that these two lines are parallel because we've learned, not just that they look parallel, because there are times they look parallel and they're really not, but we've learned that if you look at the slope of the two equations, in this case the slope is 1, m equals 1 for both equations, so the slope is 1. When we have the same slope, the lines are parallel. So we know for a fact that these will never intersect, and so this has no solution. You can either write no solution or you can put the circle with the slash through. So parallel lines have no solution. When there's intersecting lines, we have one solution. And then there's a time when we have every solution. If you graph a line, and then you graph the same line again, they're going to meet at all of these points. Just keeps going, right? Every single point. And it goes on and on forever, as shown by the arrows. And so when you have parallel lines, the lines coincide, and we say that they have infinitely many solutions. In geometry, you'll hear the word coincide more, but in algebra, we say it as that they have infinitely many solutions. Some people will do the infinity sign, or you can just write infinitely many. If you can read what I wrote there. I don't know why I used the highlighter, sorry. But that's infinitely many solutions. So in this first example, I want you to get used to identifying if we want to graph equations to solve, or use substitution, or use elimination. These equations are not in standard form. They don't go ax plus by equals c, like x and then y. And then, let me rephrase that. One of them is x and then y and then the number. That's ax plus by, b being 1, y equals 2. But the first equation is isolated. It's in y equals mx plus b. The y is isolated. So whenever you have one equation isolated, it may be best to use substitution, because I know that this y equals x minus. So I'm going to use substitution here, since one of the equations was isolated. If there were two equations isolated, I might consider using solving by graphing. Since they'll already be in y equals mx plus b, it might be quick. If I had two equations in standard form, I may think about using elimination. But in this one, I had one equation isolated, so I'm just going to choose to use solving by substitution. So I'm going to rewrite this as negative x. And then the y is x minus 1, so plus the y, which is x minus 1, equals 2. Combine like terms. That cancels. Negative x plus x cancels. So I end up with negative 1 equals 2. Since this statement is not true, it's false, it would be no solution. If you graph these lines, they'll be parallel. I can even tell that by isolating this second equation. If I move the x to the other side, or add x to both sides, I end up with y equals x plus 2. Notice the slopes. In the first equation, slope is 1. In the second equation, the slope is 1. And that's why I know that the lines are parallel, and therefore there's no solution. So if you notice that prior to even starting the problem, you can just write that there's no solution. Showing work is always best, of course. So in this problem, I have already isolated equations. This might be a good one to graph. I'll drag a graph in here in a second, but I do want you to notice that the lines definitely are not parallel, and they're not the same equations. If the lines were parallel, there'd be no solution. If the equations were the same, there'd be infinitely many solutions. So I already know that this is going to have one solution. So if it asks me how many solutions, I just already know that there's going to be one solution. If I'm told to solve, I'll do out my work. So I'm going to do it by graphing. I'm also going to do it by substitution. Let me show you. Y equals x minus 3. That means I'm going to start at negative 3. And my slope is 1, so I'm going to rise 1, run 1. Oops. And that's my line. If we're really good, we write the equation next to it. So I'll write y equals x minus 3 right there. And then I have negative x minus 1. So I'm going to start at negative 1. And it's a negative slope. It's going down 1 to the right 1. There's my solution right there where the blue and red met. So here's my other equation. This is y equals negative x minus 1. And my solution is at 1. Actually, let me put that somewhere else. My solution is at 1 on the x, negative 2 on the y. So it's definitely one solution. 1, negative 2 is the solution. And I can also do this by substitution. Since the y is already isolated, I can drop this stuff in the y spot. So I have x minus 3 equals negative x minus 1. And I could start solving, add x to both sides. 2x minus 3 equals negative 1. I wanted to get the x's together. That's why I moved it to the other side. Now I want to get this negative 3 out of here. So this is the 2x I'm solving for. Add 3 to both sides. I get 2x equals 2. Divide both sides by 2 to isolate the equation finally, and x is 1. X is 1. That's what we wanted. So if you look all the way back up here, x is 1. And now I can plug that back into either one. So if I plug it into the first equation, let me get my pointer out since I'm out of room here. If I put a 1 right there, 1 minus 3 is negative 2. Or I could put the 1 right here if I wanted to. Negative 1, since I'm putting it in front of the negative, or behind the negative really, negative 1 minus 1, which is negative 2. So no matter which way I do it, graphing, substitution, it's 1, negative 2. And I knew it was going to have one solution because it's not parallel and it's not the same line. Here we have one isolated equation. So if I want to, I can take this y stuff and plug it into here. So y equals 2x plus 1, I'd replace that y. Since there's something in front of the y, that negative, I'd have to distribute. I'd put it in parentheses. So I would write 2x minus 2x plus 1, close parentheses, plus the other 1 at the end equals 0. And I'd start solving this. Distribute 2x minus 1 plus 1 equals 0. And combine like terms, 2x minus 2x is nothing, 0. Negative 1 plus 1 is 0. So I end up with 0 equals 0 when I combine like terms, which is a true statement. And that's why it's infinitely many solutions. Infinitely many solutions. Okay, the other thing I could do is isolate both equations. So that my first one was isolated, y equals 2x plus 1. And if I start isolating the next one, I have 2x minus y plus 1 equals 0. I can actually just add y to both sides to make my life easier here, since it's negative right now. And so I end up with 2x plus 1, since the y is canceled, equals 0 plus y is y. So y equals 2x plus 1. These are the same line. If y equals 2x plus 1 and y equals 2x plus 1 were graphed on a graph, we'd be drawing the same line over again. Oops, if I could draw the same line. And so it would hit at all of these points. And they keep going on and on forever, so there's so many solutions where they're intersecting. They're intersecting at every point.